Hello and welcome back to the Cracking FAANG YouTube channel. Today we're solving 278, first bad version. This question is really good for learning binary search. You are a product manager and currently leading a team to develop a new product. Unfortunately, the latest version of your product fails the quality check. Since each version is developed based on the previous version, all versions after a bad version are also bad. Suppose you have n versions, 1, 2, ... n, and you want to find the first bad one, which causes all the following ones to be bad. You are given an API, boolean is bad version, which returns whether version is bad. Implement a function to find the first bad version. You should minimize the number of calls to the API. So for example, if we have n equals 5 versions, and the first one that's bad is 4, so the first version is good, the second version is good, third version is good, fourth is bad, and fifth is bad, because it comes after a bad one. So if we were to ask, is the third version bad? Then no, because it's good. If we recall the fifth one, that one's bad, but that doesn't tell us anything. We actually need to find the first one. So what we could do is we could just start at the beginning, and for every single version, just ask if it's a bad version, the first one we find. There you go. That's our solution. Obviously, it tells us to minimize the number of calls to this API. It could be the case that the bad version is the very last one, so we'd have to make big O of n calls, so basically one for each version of the API, which is not very efficient. And the reason why I said this is a binary search question is because if we, land on this one, let's say, and we know that it's good, there's no point in checking anything to the left of it, because if this one's good, then every single one before it must be good. And similar, if we know that a version is bad, there's no reason to check anything after it because everything's going to be bad. So we only need to check to the left when we find a bad version and check to the right when we get a good version. So basically, this is essentially a binary search, right? We'll start our left pointer at the 0th index, the right pointer at the end, and then we'll calculate the midpoint. We'll see, is it good? So if it's good, then remember we search to the right. If it's bad, then we don't know whether this is the first bad version, so we actually need to keep moving to the left to see if we can find a leftmost one. And then we'll move to the left and we'll update, our left pointer, our right pointer, and recalculate the midpoint until our binary search basically ends, and the result of our binary search will be the solution. And instead of a big O of n runtime, like with the naive solution, we'll actually be able to achieve a log n runtime here, which is what the interviewers want. So let's actually go code this up. This is your standard binary search. This may be your first exposure to binary search, so I'll go through it slowly. If you've never seen it before, it might be a good idea to, after you see the solution, to literally go through the code line by line, updating L and R manually, so you can see what each value is, what the midpoint is, how we're moving our pointers to do the binary search, and how we get our final answer. So let's now code it up. Okay, we went over the basic intuition. Now let's actually code it up. So to do a binary search, obviously we need 2 pointers, left and right. So the left will always start at the start of the array, which is index 0, and the right in this case is going to start at n, which is the last version that we know of. So what we want to do is we want to say while left less than right. We obviously don't want to just recalculate things once these pointers cross over. That will be when we get our solution. Okay, so we're going to say that the midpoint is going to be what? Left plus right, left plus right, and then divide by 2. So that's going to be the midpoint. And we're going to ask ourselves, if is bad version, whatever the midpoint is, what's going to happen? Remember, if we have a bad version, it's not guaranteed to be the leftmost bad version. We want to find the first one. So we actually need to shift our search to the left. And the way that we're going to do that is we're going to bound the right index to say we're only going to consider up until the right midpoint, right? So the right will only go up to the mid because we know that everything to the right of mid will now be bad. If the current version is bad at mid, then everything to the right of it, by definition in the question, must be bad as well. So there's no reason to check any of that stuff. It's not going to give us our solution. We only want to check from whatever left is to whatever the midpoint is, which we already just checked. So we set right equals to mid because that is the like maximum right bound we have. Otherwise, it must be a good version. And if we know it's a good version, then everything before it was also good. So there's no reason to check any of that. So we're going to say left equals to mid plus 1 because there's no reason of checking mid again. Now, you might be wondering, why is it right equals mid and not mid minus 1 like we have the opposite here in left? Because we don't actually know whether or not this mid is our solution. Remember, it could be the leftmost one or it could not be. So the reason we don't do mid minus 1 is because actually if this is our solution, we don't know it yet, but it could be. If we did right equals mid minus 1, then when our loop ends and we return what our version is, we will be off by 1 because we will have gone mid minus 1. So we'll miss actually our solution and we'll be pointing to a good version. So once this binary search ends, we simply just need to return the right index, and this is where our solution will be, because remember, we're setting right equals mid to do this. So it's either going to be contained in right, or yeah, it will be contained in right because it's guaranteed to exist in there. So again, that's the reason we don't do mid minus 1. In some binary searches, you might see mid minus 1. That's a completely different case. Unfortunately, there's no one size fits all approach to binary search. The general kind of formula is always the same. You're going to have a left pointer, a right pointer. You're going to have this while loop, but sometimes the while loop will actually be less than or equal to. Sometimes you'll be returning from within it. It's really up to each question, and this is one where you actually want to move the pointer, and depending on where it ends at the end of the array, once the loop ends, is what you return. So they're not all the same, unfortunately. You will have to do enough of these to get familiarity, but this is the general rubric that you can use for binary search. So let's just run this, make sure it runs. Looks good to me. So, and it was accepted. So what is the time and space complexity here? Well, like we already talked about, this is a binary search. So our time complexity is just log n every time we cut down our space in half. So this is a log n solution. For the space, we don't use any space except for these two little pointers here to store our right and our left. So this is just going to be big O of 1 space. So that is how you solve first bad version. This is a really good introduction to binary search, relatively straightforward. I like this question a lot because it gives you exposure to a binary search where you're not necessarily returning a value within the array. You want to complete the binary search and then return the value of one of the pointers. So it's a good exposure to that one because it is a little bit harder. If you didn't understand this one, this is a perfect time to take a step back and draw out an example and update left and right as you go through this array, what the midpoint is, and see if you can't, sketch it out and see how it works. I think it's a good opportunity to build that muscle because sometimes you do need to do that to actually understand a question. It's not always the case that you can read the solution or watch one of these videos and get it. You may need to actually write it out. So this is a good time to do that if you need to. Anyway, I've rambled enough. If you enjoyed the video, please leave it a like and a comment. It helps me grow. Otherwise, subscribe to the channel to help me grow, and I will catch you in the next one.